Okay, so here everyone, today I'll be doing the week 9 physics quiz. I'm sorry my SDP wasn't working. I have no idea why. So I'm resorting to the PDF file and it took me a while to actually get started with everything. So question 1, a loop ABCD is rotating between the poles of permanent magnet. So first of all, I already drew this out. You can see that this is my magnetic field. It's going from north to south as always. Now you guys should know that when it's 90 degrees, this is 90 degrees equals the flux change to be 0. Right? And when it's 0 degrees, it is maximal. Okay, now that we know this, here you can see that it is making 90 degrees with the magnetic field. This means it is, by the way, we're talking relative to the magnetic field, not relative to the plane or relative to anything, not relative to the normal. We're talking about the magnetic field. You can see it's making a 90, which means that change at the fact that is horizontal means that it is going to give me a 0 flux change. Now, we also see that it is rotating like this. Okay, so that's what are the phases. So this is what. Then it's going to rotate, let's do a quarter of a turn by 90 degrees. Then it's going to rotate a quarter of a turn by 90 degrees, and then another quarter 70, and then the full 360 rotation. Okay, this is how it's rotating, right? Every 90 degrees, it's like this. You can see here, let's take this one to be positive. Let's take it to be the positive, positive direction. Okay, here this is our first direction, right? You can see here it changes like negative. يعني it was going like this, right? Then it went like this. I'm taking arrow to be positive sense. Now it is going like this, so it is negative, right? So we want positive to negative, right? Then the arrow flipped up like this. I'm just putting an arrow here. يعني this arrow doesn't exist. It's an imaginary arrow just to show you the direction. It's going like this, the arrow is going up, then it comes back down to this, it changes positive again. So our first change was from the positive sense to the negative sense, and then our second change was from the negative sense to the positive sense. So you can see that at every rotation, it changes its direction twice, from positive to negative, then again from negative to positive. And since we're changing, right, if you were to graph the current, right, since it's alternating and all of this, if you were to graph it, you would get this graph. You would get something like this. You would get something like this. Okay. Now, what this is a sine wave. Okay. Now, this is an indicator of, especially in electricity, this is an indicator of an alternating current. And since it's alternating its direction, something is alternating, obviously it's going to be alternating its current from negative to positive. As you can see, it goes from positive to negative to positive and over to negative. It's just a regular sine curve. Okay, so then we can conclude that the rate of the flux change through the loop is 0 when it's horizontal. We answered this. The current generated is called alternating current, and it changes its direction twice every complete rotation. Okay, question 2. The magnitude of the magnetic field created by a current carrying wire at any given point is directly proportional to the current in the wire and inversely proportional to the distance from the wire. Now, this is purely logical because if you think about it, right, we know that the magnetic field, right? Let's think about this from a logical perspective using the right hand rule. Or Fleming's left hand rule, they both work. You find the direction of the force by combining the magnitude of the or finding the direction of the magnetic field and the direction of the current. Yani this would logically indicate that this is that the magnitudes of these are proportional. Now, this is also logic. Yani if it's the weaker the magnetic field, the longer the wire is going to be, right? Because it's going to be distributed over a longer distance. Yeah, مثلا, so you have the unit of the magnetic field is Tesla. So let's say you have a magnetic field of 1 Tesla, right? I would, like, honestly, logically, 1 Tesla over this distance is going to be distributed. So yani each point is going to have a greater force of magnetic field compared to 1 Tesla of a wire that's this big, for example, because each point, like for example, this point will receive less current than this point, because he or less Teslas. This would have a stronger magnetic field. This would have a stronger magnitude. So the distance from the wire and the distance in the wire actually is inversely proportional, and it's directly proportional to the current in the wire. Now, which of the following are turned or true for a galvanometer? Okay, we're talking here about galvanometers. In a galvanometer, this is wrong. I'm going to start by using our options. The more turns a galvanometer has, it's actually more sensitive. Not less, more. It is because it is going to pick up more current as it goes. A galvanometer loop must be placed in a radial magnetic field. A magnetic field induces the torque on the current carrying coil of the galvanometer. And the coil of a more sensitive galvanometer contains a spring with a smaller spring constant. Okay, the greater the magnetic field a galvanometer is placed into, the less sensitive it is. This is incorrect because it contradicts the statement if you think about it, right? Here it says a magnetic field induces the torque on a current carrying coil of a galvanometer. All a galvanometer does is it carries current and it measures it. You can't set it to measure it. Right? So first of all, this is why this is wrong, because it's gonna pick up more current, as I said, with more coils. So it's gonna have each coil is gonna pick up more current, which makes it more sensitive. Now here, going back to these two, a magnetic field induces the torque on the current carrying coil of a galvanometer. If it induces the torque, and the greater the magnetic field is, so it's gonna induce a greater torque, a greater moment on the galvanometer, right? It's gonna make it more sensitive because it's again picking up more current. Because again, we just said it in the previous statement, it is directly proportional to the current and inversely proportional to distance. So the more magnetic field, the more current. The greater the magnetic field, the greater the current, which makes a greater torque. So it's going to make it more sensitive, not less sensitive. The statement is incorrect. Okay, question 4. If it loads, I don't know why it's not loading. I don't know why the whole thing's bugged. There we go. Okay. Here we're talking about electromagnets. Let's draw out an electromagnet first of all. So, an electromagnet is a series of coils wrapped around an iron core. It is like this. This is like, for example, this would be a weak electromagnet because it doesn't have that many currents, or that many coils, sorry. Electromagnets are made by winding a current carrying wire. This is correct, again, because this wire is supposed to carry current. That's what an electromagnet is. Around an insulating core. This is wrong, because it is a conductive core. Electromagnets are permanent magnets of fixed strength. Their strengths are variable. This is incorrect. And also they're not permanent because you can turn them on and off. Electromagnets stop being magnetized when current flows through them, that current flowing through them is off. Yes, because an electromagnet is, again, a current carrying wire wrapped around an insulating core. When there's no current in the current carrying wire, what's the point of the electromagnet? It's going to be turned off. Statement's correct. The role of the magnetic core is to increase its magnetic field strength. Yes, because it makes an induction, it induces, which generates an alternating current, by the way, into the magnetic field. The direction of the electromagnet field can be changed at will. Yes, because I can flip the direction of the coil, and I can flip the direction of the core, and that would flip its directions. Okay. Question 5. I don't know why it's like lagging. Let me just pause until it loads everything. Okay, so question 5. The magnetic flux through region A is defined as the product of the magnetic field and the projection of the area of the region perpendicular to B. Now, so we're going to think about the previous example, the perpendicular part, right? Here, remember, first of all, we're going to have to recognize the formula. The magnetic flux, which is denoted by phi, is BA cosine alpha or theta, whatever. Okay, now, we're just going to interpret this into this. The magnetic field, phi, is defined as the product of the magnetic field, B, which is a vector, but you should know that, and the projection of the area, A, of the region perpendicular to B. This is where the cosine alpha kicks in. You can also write normal, and this is an accepted answer, by the way. They are both the same thing. Because if it is normal, it would just be BA. thus يعني you measure it using the perpendicular region to fully define this, right, without the cosine alpha. Now, question 6. In which of the following electric devices does the current change its sense? When we say current changing its sense, it means it's alternating. Therefore, alternating current, which I will remind has the graph of a sine wave, which alternates positive to negative to negative. Okay, now to achieve this current, we're gonna use certain tools. We're gonna use a twin generator. I'm just gonna check them here. Generator. Also, we use a split ring or slip ring commutator. Okay. Now, these two are used to achieve electric or alternating currents. A simple dynamo. Now, you can look up what a dynamo is, but I'll give you the simplest example. Think of a bicycle. You know how in like a science lab or a science exhibition in a museum or science museum, you have this bicycle, right? That when you pedal, the more you pedal, let this be the pedal, it powers more electricity into a light bulb. And the more you pedal, the brighter the light bulb is going to be. When I pedal, right? When I pedal, and I pedal at my maximum, it's gonna be here, right? I'm like, think of it, look at the sine wave, it's gonna be here. The light bulb's energy is gonna be here. The current is at its maximum. However, when I stop my pedaling, would it stay at this point and stay as a straight line? This would define a DC current. A DC current line is, by the way, it's just a straight line. It could be anyway, but it's just a straight line. However, AC is alternating. No, when I stop pedaling, when I stop this pedal, I stop this motion, this will receive no current. Therefore, it alternates all the way back down to here, which means that it is an alternating current. And this is a simple dynamo. This is the true definition of a simple dynamo because it has nothing added to it. It's just a bicycle connected to a light bulb. So we could also use a simple dynamo to change the sense of the current. And we could also change it to negative because essentially a light bulb uses AC current anyway. Now, which two different methods of generating electricity are illustrated below? Which method or which generator generates an alternating current? We said we use slip rings to make AC. These are brushes. These are used to make direct current. That is BC. I don't know what BC is, but DC. There we go. These are just normal brushes. These are made of carbon, by the way. They will tell you it's a carbon. And this is a split ring commutator. Keep this in mind. It's not a split ring generator. It's a split ring commutator. Okay. The difference is one generates and one flips around. It's like I can't really explain it in the scope of like 3 minutes. So we're just gonna ignore it. We're gonna focus on this. Slip rings. Straight away when you see slip rings, assume AC. So alternating current. You have slip rings, generator, and A. Current in one direction, this is DC. If you see the brushes, it's going to be DC. خلاص. Simple. Question 8. A coil is rotated in the presence of an external magnetic field to produce electricity. The output voltage of the coil is shown below. This is an alternating current, as I've said many times. When is the surface of the coil perpendicular to the magnetic field? Remember, perpendicular, so like this, means the magnetic field, by the way, it's always been the magnetic field. Even in the first question, remember, it was going down like this, and it was horizontal, it made 90 degrees. That means that it is going to be 0, because remember, cosine alpha, which would be 90, cosine 90 equals 0. So we're going to look for the point where the current is 0. We have it here at this point, we have it here at this point. Now, if this point was labeled as, let's say, point E, we would have it as also here at point E. However, point E is not labeled, so we're going to ignore this. So we trace it. It goes to point A and it goes to point C. So when it is perpendicular, which means it's going to have a 0 current, it is at A and C. When is the surface of the coil parallel? Parallel, remember, it would be, they'd be in the same direction, so it would have like a 0 degree or a 180 degree. It could be 0 degrees or 180 degrees in between them, right? So what's the difference? Because cosine 180 is -1 and cosine 0 is 1. So in an alternating current, this actually helps us because this is where it would be in the negative direction. Right? This would be where it's like in this area here, in the negative part, which is this place. And when it is 1, right? When it is 1, it would be in the positive direction. Now this is where they would be. Okay. Now we also have to remember that at 1 and at negative 1, you would have maximal output of current, because you're multiplying it by 1. You're not multiplying it by 0.8 or 0.5. You're multiplying it by 1, so it would only be B times A, right? So making this at the peaks or the troughs. So the highest points or the lowest points of the graph. So the highest point on the graph is B, here, B, and the lowest point is here, the trough is D. So it is at B and D. Okay, which of the following statements are true about the simple AC generator? Straight away, when you see twin ring, always assume AC, so this is correct. And the simple generator, the magnet rotates about stationary coil. Now, this is not how it works. So I'm not gonna go into detail, but this is not how it works. An AC generator can contain either a permanent magnet or an electromagnet. Remember, we said an electromagnet from the previous question. It is not permanent. It can be switched off. So this is also correct, though I just wanted to differentiate further to explain it further. An AC generator can include a permanent magnet or an electromagnet. An AC generator can either include a slip ring or a split ring commutator. As we saw in the previous question in generator B, they used split ring commutators, right? They use split ring commutators for the DC current with the brushes. So this is incorrect. This part can only be used for the DC, so this is wrong. If the loop of the generator moves uniformly, the current generated varies according to a sine function. Yes, as this is AC. AC, remember, AC is a sine graph or a sine wave. Question 10. The peak current in an AC circuit is 20 milliamperes. The RMS is 2 decimal place. Okay. Anything RMS, let's label anything as Q for quantity. Quantity RMS, in terms of physics, as far as we need to know, is the peak quantity, QP, over radical 2. So here we're talking about the current, right? Yeah. So IRMS is equal to, RMS means root means square, by the way, is equal to the peak current over radical 2. So IRMS is simply equal to 20 over radical 2. You do this on a calculator, you get 20 over radical 2 gives you 14.1. So the actual answer is 14.1 because they wanted to do decimal place, but I'm assuming they do accept 14 since it's in the answer key. Okay. Now, here, this is a direct current. Okay? Because again, we have the brushes and we have the split ring commutator. So straight away, this is wrong. And this here is wrong. Okay, this doesn't really make sense because what happens in this interval, it is incorrect, leaving you this region only. Okay, on to question 12. Name the parts of a transformer, give the function of each. So a transformer is essentially like this. It is a coil connected to an iron core, connected to a second coil. By the way, the coils are supposed to pass through, but I don't know why my tablet's lagging. So it doesn't, but whatever. This is an inaccurate drawing. First of all, we're going to start with the iron core, the easiest one. Helps in linking the magnetic field of the primary coil with the secondary coil. Yes, because remember, they are both joined to the iron core. So this is the soft iron core. Now, it starts by generating an alternating magnetic field, passes it through the iron core, and then passes it through the secondary coil. And even then, so what helps with generate the alternating is the primary coil, which is what I just explained. Even then, well, that leaves the secondary coil. Even then, you can see here, helps in linking the magnetic field of the primary coil. So when you have a magnetic field, it's always say primary coil, and this results in the EMF in the secondary coil, which is the voltage. This is, there are two different types of transformers, the step up and the step down, which is what we're going to explain now with the step up and the step down. So based on the number of coils, it is a step down transformer. If the primary coil has more turns, okay, than the secondary coil, so PC greater than SC, it is step down. If the secondary coil has more current or more turns than the primary coil, it is step up. Okay. There are formulas for this. So for the transformer, Okay, it would induce voltages. So you would have V2 over V1 equals to uh, the number of turns in the secondary coil. 2 is the secondary, by the way, over N1. And friendly reminder, yani, I don't think it's just take as an additional side note equal to the current in the primary coil over the current in the secondary coil. Okay, although I'm not sure they'll ask you about this because they didn't ask in the quiz. What's the number of turns in the secondary coil? You apply the formula. So we have our voltages here. So this primary is 48 volts. The secondary is 240. So 240 over 48 is 2. How turns we're going to be all turns in primary of FC. So this is equal to 240 times T divided by 48 give you X to be 300. And the primary coil and the current secondary coil is 2 amperes. Put power on transformer. Now, you know that P equals IE. Okay, so at this stage, P equals IV. All you're going to need to do is multiply. P is equal to IV. Why is it such a low office? So power equal to M power. So the input of the transformer means is the primary. So is 4 amperes times how much voltage we have? We have 48. This gives me 4 times 48, 19 watts. Okay, what's the output power transformer? 0.2 amperes times 240. This gives you on a 173 watts. So that's P2 power of the output power over the power of the input, or P1 is 100. So it's going to be 173 over 192 times 100, which equals to 90.1 or 90%. Okay, just take the power of the primary, which is 90.2, 19.8. And the secondary course is P1, P2. This is milliamperes, so this is 162 times 10 to the power of negative 3 amperes. So this is 162 times 10 to the power of negative 3 amperes. Times 110 volts, which equals to 162 times 10 to the power of negative 3 times 110, which gives me 17.82. So then 17.82 over 19.8 times 100 equals to times 100, 90%. Okay, on to question 16. RMS voltage. Now, the RMS voltage is essentially the useful voltage or the output voltage, right? So here we said it lights up as a 12 volt battery. So the useful voltage is what's actually being used by the light bulb to light up, which is 12 volts. Okay, now the peak voltage. Remember, we said that the RMS is the peak over radical 2. So the RMS is 12. 12, we don't know the peak. VP over radical 2. So VP is equal to 12 radical 2, which equals to 12 radical 2, 16.97 or 17.0. It's fine. Here they did 16.8, but the thing is, they used, I think, 1.41 or something. They didn't use the exact value of radical 2, which made them get a lower answer. So, an alternating current is generated in the coil when the coil rotates relative to the poles of a magnet. The current is taken out through a twin ring commutator. Whenever you see twin ring commutator, خلاص, alternating current. So these two like get themselves out. Now, think about it logically. What do you have to do with a transformer in an alternating current? What do you have to do with a resistor in an alternating current? Pretty much it's only a magnet, right? Because it is relative to the poles of the magnet. Again, this is how to like think of it as an electromagnet. It's a soft iron core or which is magnetic. Okay, when you take out, you're gonna it's negative, or by Lenz's law, يعني it induces the opposite. You know, Lenz's law acts on this, and it acts in the opposite direction. So, going to induce positive, and then it's going to induce again when it goes back in. It's going to induce a negative, which makes it an alternating current. Okay, the front screen of an oscilloscope is imprinted with a grid. The horizontal scale has units of time and the vertical scale has units of voltage. This you memorized. I can't. An oscilloscope is used to measure voltage, and it's a good device for this. If you have, really nice. If the secondary coil has more turns than a primary coil, then the transformers will step up. Remember, we said secondary coil SC, grade PC equals to step up. when transfer ratio is less than 1, it's called the step transformer. Okay, this is similar, right? Remember, it is n over n equals to v equals to v1, whatever. This is equal to the transformation ratio, so this is known as m. Okay, now this would mean, right? Think the n is the number of turns, right? So think about it. Let's say the second turn had 75. Okay, for 75 turns, first the secondary current or secondary coil, and the first one at 150. This is gonna equal to a value less than 1, right? And you know this, the turns in the secondary coil, if it's less than the turns in the primary coil, it would give me a step down transformer. So this here, this is turns in SC, here in PC, SC is less than PC, which makes it step down. Step down. Okay. ID transformers primary or secondary coils of 160 and 800 turns respectively. The AC voltage is 270 volts. What is the output? Okay, at the output it is 270. So first of all, 270 V2 over V1, 270 over X or V, doesn't matter, equals to 4800 over 160. And by the way, if they ask you what generator is this, it's a step up. Now 270 times 160, you do the ratio, 270 times 160 divided by 4800. 270 times 160, divide this value by 4800, you get 9 volts. Okay. This you apply the right hand rule. So actually, by the way, for questions like this, since it's hard to like do I, B, F, you know, that way, but you could, I just did it with the right hand. You could do it with your left hand. Your thumb is, I'm going to explain it with the left hand rule. It's easier to see. The left hand, the thumb, okay, your thumb is the force. The finger after your thumb, the first finger out of your thumb is your, like right now you should have a finger gun. The first finger out of your, beside your thumb is the field, and the second finger is the current. Okay, right now you should have a finger gun with 2 fingers. So the current is the second finger, so I, the first finger is the field, and then the force is going upwards. Yes, the force is going upwards. So that's it. Now, the device shown is a DC electric motor because this doesn't have split ring or twin ring commutators, whatever they're called. So it is DC. The side A experiences an upward force. Yani, this is another right hand rule. I can't explain it over video, inshallah, but when I do a face review or what was it called? Face cam, I will extend the right hand rule. So this is upwards. Okay. Same thing with the voltages of the transformer. The output in the ideal transformer is 12 volts. The primary is 100. The number of turns in the secondary coil is 650. Okay, so 12 volts in the input. So this is at the bottom. Never mind. This is going to be V over 12 equals to 650 over 100. So then 650 times 12 divided by 100 gives you 650 times 12 divided by 100, 78 volts. Okay, then the number of turns. SC is greater than PC, so it's a step-up transformer. Now, a transformer has 300 turns in the primary coil and 50 turns in the secondary coil. The current in the primary coil is 5 milliamperes and that in the secondary is 27. Okay, you know that it is P2 over P1 times 100. Okay, P2. Now you don't have voltage, so what you can do, remember that V2 over V1 equals to, or that's multiplied, equals to N2 over N1, where N is the number of turns. What is P? So it is I1 V1 over I2 V2 times 100. This is the efficiency, right? Because this is, I just expanded P. Now, V2 over V1 is, or sorry, this is actually the other way around. This is V2. Let me just erase this. It is I2 V2 over I1 V1. And you can split this fraction up, right? So it would be I2 over I1, right? I'm just splitting it up into fractions. Into V2 over V1, right? This is easy. Now, remember, V2 over V1 is equal to N2 over N1. So this is actually I2 over I1 times N2 over N1, which equals to, we have I2. I2 is, obviously all times 100, but we'll multiply by 100 later. I2 is 27. I1 is 5. I'm getting my values from here. And then 50 turns in the secondary over 300 turns in the primary. So